Right. So so I'll just go on with what I was talking about yesterday. So maybe I'll start recalling the Boltzmann equation. So what we did yesterday was basically sketch in some way why this equation, which is the Boltzmann equation, should be in some sense a limit of the particle system. Remember, we had those hard spheres. I won't go through that again. And we had the one particle correlation function that converges maybe, and if it does converge, it converges to a solution of this equation. So let me just recall Q of FF here is. So by construction, we had the integrals. So let me be a little bit more precise maybe than yesterday. So you had velocities chosen randomly in RD, an angle in SD minus 1. And so the measure here was, let's say, if this is a function of x and v, x doesn't move anyway here, but okay, then you integrate over v1 over omega, which is the angle. Then you have this cross section, v minus v1 omega plus, positive part of this the scalar product. And then you have in a sketchy notation, which people always use, which I'll be explaining again, this quadratic term. So f prime 1 is not a derivative of f, it's f of v prime 1. Okay, and x doesn't move, so just put x here. F prime is f of v prime. Okay, and f1 is f of v1. It's just a short notation for all that. So this is Q of FF. So essentially what you're saying, when you read this term, you see that you have binary collisions. So what I didn't say yesterday is that if three particles collide at some time or even more, but that just never happens, or almost never. The set of initial data for the particle system that would create more than two particles colliding at the same time is of measure 0. We just forget that. So that's why I have only binary collisions, so a quadratic term here. Remember, maybe v prime 1, v prime are pre-collisional velocities before collision. Remember that drawing? So this is pre-collisional, and here I have f of v1. What I'm saying here is that you can create particles with velocity v if a particle of velocity v prime hits a particle of velocity v prime 1. And that creates a particle of velocity v. That's why you have a plus sign here, essentially. And you can lose, by this term, particles with velocity v if they collide with a particle of velocity v1. That explains the plus and minus signs here. Right, so maybe just a few words on this equation. It's a very important equation. It does converge in some sense to fluid mechanics equations, as I said yesterday. But maybe let me just give you a few interesting maybe information on this equation. For instance, one question you could ask are what kind of quantities are conserved? If you want to solve an equation, you like to know what's conserved. And so one thing you could check to do that, for instance, if you want to know that f of txv tested against some function phi of v, for instance, dxdv, you would like that to be, okay, do you have functions phi such that this is true? So what you do is you take phi, you plug it into the equation, integrate by parts, do all kinds of things. And what you find that you would need to be true that Q of FF phi dxdv, this should be 0, right? If you want this to be conserved for any f. And so if you compute this, you just multiply Q of FF by phi, you integrate in v. So now you're integrating in v and v1, right? And you see everything is symmetric in v and v1. Okay, so it's actually the same as half of Q of FF. Let's use the notation phi plus phi 1. Now what you could also do is exchange vv1 into v prime 1, up to changing omega into minus omega, which doesn't do anything. So actually what I can do here, up to a minus sign, is putting minus v prime 1. When is this 0? So there's an obvious case when this is 0 for any f, is when phi is a constant. Okay, so that works. So if phi is equal to 1 or any constant a is a constant here, then you get 0. If phi is a constant, you see what you're doing here is just saying mass is conserved. Integral of f is conserved. There's another case when this could be 0, is that when phi is equal to v, because then you get v plus v1 minus v prime 1, and that's the conservation of momentum. 0, so if phi is any linear combination of v for v any vector, then you also get 0. Now, obviously, there's another case where that works, is when phi is also conserved when you have a collision. So you're also allowed a quadratic term in v. And actually, it's a theorem. It's not very hard to prove if anyway, at least if phi is smooth. It's the only way to cancel this guy for any f. Okay, so what we retrieve here is conservation of mass, momentum, and energy at the mesoscopic level, which is nice. That's all you get for conservations in this setting. What you could also do, you see this formula, you could think maybe you could want, I don't know, to choose for phi something a little bit special. You could say, look, let me now choose for phi the log of f. Okay, f is not negative. Let's take that for fun. Okay. And then you see here what you get is something like, well, actually exactly cube ff, and then using nice properties of the log, you get something like this. Now, exercise, this is negative one, is non-positive. Here is that when I go back to this computation here, what you've sort of proved, at least if f is smooth enough, is that the time derivative of f log f. So that's the H theorem of Boltzmann. H is for not entropy, but entropy, actually. I think eta, capital eta in Greek is an H. So that's why this is called the entropy, and it's called H. And so Boltzmann actually did this computation. He said the entropy for the Boltzmann equation decays in time. If you're a physicist, you would say it increases, right? Because they put a minus sign in front of the entropy. This can be useful. That's a way you can construct weak solutions, right? Even renormalized solutions using these bounds on F, which I won't explain today. But I just we want to point out something which is, I guess, important, is that when Boltzmann wrote down this equation, wrote down the H theorem, people were very upset because you get a quantity here which is decaying in time, whereas the particle system is time reversible. Okay, you just exchange time, exchange the signs of the velocities, and nothing happens. Okay, the sign of time and of velocities. And now here you have something which is decaying in time. So Boltzmann equation is not time reversible. So that was a big panic situation at the time. A lot of controversy between, I think, Loschmidt and Boltzmann in particular. And actually, it turns out there's no incompatibility between this being not time reversible with Boltzmann equation and the particle system being time reversible. And that can be even understood in the proof Landfall Theorem. So the question of irreversibility happened. How come the Boltzmann equation is time irreversible and the particle system is time reversible? One way of understanding that is to say, if you want to prove the Landfall Theorem, which we won't do, but I sort of explained yesterday that one very important thing is to prove the propagation of chaos, remember? Which says that if two particles meet, well, they haven't met before. And if I say they haven't met before, I'm saying I have an arrow of time. Okay, if they meet, they meet. Okay, and they haven't met before. Now, if I do that the other way, two particles that have met will meet. Oh, two particles. Okay, nothing. Forget what I was going to say. But anyway, this sentence definitely has a time arrow. Okay, and so one thing I could do, but I really don't have time to do, but you could write down the statement of Landfall Theorem in a totally time irreversible way. It's obvious that the way your initial data is set up and the way the solution converges to the Boltzmann equation, that's totally time irreversible. So we can talk about that at some other point if you want, but so it's really related to something which is called recollisions. We'll be talking about that today. Landfall does not want recollisions. Two particles that collide cannot collide later on. Two particles that collide cannot have in their collision tree, meaning all the particles they've seen before, any particles common in the two collision trees. Okay, so recollision is just not allowed. And when you say a recollision, you're specifying the arrow of time. Okay, so there's no paradox actually in this situation. That's about all I wanted to say. I thought I might mention a little bit about hydrodynamical limits at some point, but maybe later on. But I did mention it a little bit yesterday. But it is well known that behind this Boltzmann equation there is compressible Euler, there is incompressible Navier-Stokes. Behind linearized or linear versions of this equation, there's the heat equation, there's the Stokes-Fourier equations. A lot of fluid mechanics equations are hidden there, and there are a lot of theorems going from Boltzmann to those fluid mechanics equations. But again, as I said yesterday, those theorems require to have a large number of collisions in the sense that, oops. Remember I had said you have to put something like this with alpha going to 0, and then the time on which Landfall Theorem is true just breaks down when alpha goes to 0. Now, so what I want to talk about today are fluctuations around the Boltzmann equation. So remember, I defined yesterday the fluctuation field for any test function h to be so some kind of zoom square root of n or square root of u epsilon. U epsilon is the average number of particles, and it's equal to epsilon to the power minus d minus 1, which is the Boltzmann grad limits of dilute gases. So what you do is you take your empirical distribution at time t, computed at h, you remove its expected value, and you would like to know, does this have a limit as epsilon goes to 0, as mu epsilon goes to infinity? So as we did yesterday, we could start maybe with the exercise of looking at the time 0 situation. So I apologize again for people who would know that very easily. For me, it was not so easy the first time I saw it, and I like the proof, so I'll do it again for you. Let's compute what happens at time 0. Let's try to do that. Yeah, that's right. So let's try to do this. And actually, what I'm going to do, what I want to prove is that this, at least at time 0, is a Gaussian field. Let's compute its covariance or variance. Okay, so let's see. So what I'll do, just to show you a little bit about scalings and stuff, and it is sort of useful as a computation, is compute this thing, which would be time 0 exponential of this guy, right? And what I want to prove is that there's only the order 2 term that comes out. Okay, so that will tell you to have mean free, and you can compute the covariance. If you compute the limit of that, as epsilon goes to 0. So I'll actually compute the expected value of this guy. So you probably have forgotten the formula, but I'll recall that for you. So you have the partition function, then you have a sum over n. This, which came from the number of particles, and then you integrate on the domain with exclusion. Remember that guy? Then you had n copies of the initial data, and this exponential here. And then we'll compare that to the average. So what I have here is something like 1 over square root of mu epsilon, sum of h of zi, dz. Okay, tell me if I'm making any mistake. I guess I have something like this. Like yesterday, I don't like this exclusion. Okay, I didn't like it yesterday. I don't like it today either. So what I'll do is just pretend it's not there, like yesterday. Remember, the error you make is roughly epsilon to the d, which is very large compared to mu epsilon, so it doesn't matter too much. Okay, so I'll just forget that, up to epsilon to the d. And so if you believe me, you can remove that, then you know this epsilon, again, up to an epsilon to the d looks like an exponential of mu epsilon, so this is this guy. And then here, now you see everything is nicely prepared. You have n copies of f0 and n copies of this exponential actually. So it's just exactly as if you had mu epsilon, the integral of f0 of z, exponential of I over mu, square root of mu, h of z. So here have you symmetry. So I hope you agree with this computation. And now all you have to do is write down in terms of powers of mu what comes out. So the exponential times 0, when the first term will be just the integral of f0, which is 1. That's good. It cancels out with this guy. Okay, the next term will be something like I square root of mu, the integral of f0 h. This looks bad, but it's not bad because I have to remove exactly what this guy, okay, up to an epsilon. So this will go away with this guy. And now the next term, which is the one I want, is minus I, the integral of f0 h squared. Plus lower order 2. So this is an easy computation saying that at time 0, the fluctuation field converges to a Gaussian field with variance distance. So now the question we want to address is what happens when time evolves. So do we have a Gaussian field, and what is its covariance, etc. So let's see what happens as time goes on. Yes.
Is there a 1/2?
There is a 1/2.
Okay.
And there's no I actually.
Yes.
The I was just turned on. Okay, so what happens as time evolves? If I want to do a similar computation, let's just think about scalings a little bit. What happened in this computation was that what I did here is I sort of cheated saying I forget about exclusion at time 0 because it's of size epsilon d, so it's fine. It wasn't cheating, you can prove it's okay. Now, if I do the same thing at time t, what's exclusion at time t? Well, I'm going to look at 2 particles, and the question is, had they interacted in the past between time t and time 0? Okay, so exclusion at time 0 becomes exclusion of the tube of particles I'm looking at, all the tubes actually. right? And we computed yesterday the size of those tubes. The size of those tubes was epsilon d minus 1, which is exactly the size of u epsilon. Okay, so here I said I can kill those guys because it's epsilon d, so I don't care about exclusion. Now, when you look at dynamics, you do care about exclusion. Okay, you can't just kill that. So what's going to be very important at time t is to understand exactly a dynamical relation system. So what we found out for some time is that there's a very important notion which we rediscovered, very, very well known, of course, cumulants, which I'll explain. And that's really the very important, I think, feature of this problem is understanding cumulants and not point correlation functions. So let me try to explain this in two ways. The first way is a well-known computation, which I won't prove, but you can check, it's not so hard. Let's look at this exponential moment I wrote up there, maybe without the I don't really care about the I. For any function h, what I wrote before h was actually h over square root of mu, but for any function h, let's look at this. And you can compute what that is equal to exactly. Get this formula where this guy here is exactly a cumulant of order n. Apply to exponential h minus 1 tensor n times zn. This is just a computation. If you've seen it before, you say, oh yeah, I know. If you haven't seen it before, you have to trust me, but you can try it, it works very well. So what's f epsilon n? So f epsilon 1 is simply the 1-point correlation function. F epsilon 2 up to a rescaling is a 2-point correlation function. I'll define today, minus the tensor product of the 1-point correlation function, which is exactly what you're interested in. It's saying that this is just two particles correlated, and this is their independence. And that's the difference between the two. That's really what you're interested in if you want fluctuations, right? So f epsilon 2, if you compute it against a test function of two variables, is exactly 1 over mu squared. It's the value of h, the sum over all couples ij, h of zi, h of zj. I forgot to put that yesterday. Expected value. Okay, so and then if you can go on and on. F epsilon n will be I take the n-point correlation function, I remove all possibilities of 1 against n minus 1. I add all the 2 against n minus 2. Blah, blah, and this gives you the n order cumulants. But I won't need that right now. So if I want to understand the behavior of this fluctuation field at time t, if I believe the computations we made at time 0, I want to do exactly the same computation at time t. And so what's going to pop out of the computations will be this guy here, the second order cumulant. The next orders will go away just as before, because those are really lower order terms. Okay, so it's just the second order, which will be different. The second order term is precisely, due to this formula, the second cumulant here. Okay. So now the question is, what equation does this second order cumulant satisfy? And if you want to understand the equation that satisfies, what you can do maybe, just to understand what's going on, is a drawing. So what kind of drawing? You say, well, f epsilon 2, let's look at this guy first. At time t, depending on two variables, z1, z2, is given by what? If you just a graphical picture, I have time t, I have time 0. At time t, I have two particles, one sitting at z1, the other one sitting at z2. Okay, and now I want to know what happens to those particles between time t and time 0. So what's going to happen to those particles is that they go in straight lines, and sometimes they collide with other particles, which themselves collide with other ones. Sometimes you have a recollision, right? Because those two guys saw each other, and now they see each other again, backwards. That's a recollision. And the same happens to number 2. This is a typical collision tree of two particles. And now what can happen is that those two collision trees themselves collide, which is in some sense a recollision, because two particles have seen each other before and see each other again. This is a particular type of recollision where the trees actually are colliding and not recolliding. Okay, the first time these two trees meet. And then it can happen again, of course. So this can happen, or it can not happen. So then I do the same kind of drawing, but I do not want that to happen. This is really a sum, and then all kinds of things happen in the past. So a 2-point correlation function is there is a recollision between two trees, or there is not. Now, there is not a recollision is a kind of correlation between those two trees, because I'm opposing the fact that they do not recollide. So those are not independent because I'm saying they do not recollide. Okay, it's the same thing as if I write down the exclusion at time 0. I said before, exclusion at time 0 is no exclusion, 1 minus 2 particles to each other. Okay, so in the same way I can say no collision between two trees is 1 minus there is a collision between two trees. So let's do that. So again, I just want to expand the second term because my trees are still correlated in some way I don't really understand. So let's say that two trees do not recollide. It's equal to totally independent, 1. Okay, so that means tensor product. They cross or they don't cross the same, they don't see each other. Minus, they do cross, but how do they cross? They cross by what we call an overlap. That they cross, okay, so two particles will be at distance epsilon at some point, but there's no scattering because my particles don't know, that's totally mathematical. My particles have nothing to do with that. If they cross with scattering, here it is. Okay, so that means two particles cross and okay, it's a billiards. Okay, now I say they don't cross means they're independent minus they cross, but nothing happens. So it's not physical, right? It's an overlap between two trees. So once you've done that, you're done because you're saying I can compute f epsilon 2, the cumulant is the difference between this f epsilon 2, capital F. This is exactly F1 tensor F1. Okay, two particles live their lives independently. And so this cumulant here up to mu epsilon times two terms, one which is with a recollision minus an overlap. And this guy here is of order 1. Why? Because a recollision, like an overlap, costs exactly epsilon d minus 1. Again, it's two tubes that meet sometime between 0 and t. Okay, so this rescaling thing is to guarantee that this second order cumulant is of order 1. And this is not a PDE, not exactly, but you can turn it into a PDE, and that's essentially a theorem you can prove. So here's a theorem, which we got with Thierry, Laure, and Sergio. Okay, so the paper is sort of, it's taking forever to be revised. I think for the past year, we've done only revising papers, which is very frustrating. But so I guess on the archive, it's been for about 2 years. And I hope a revised version will be soon. But anyway, so it's essentially from 2 years up to now. So what's the statement? You just take the same assumptions as for Landfall. Okay, so I won't write them again. You have 0 is continuous, bounded by a Gaussian. And so what happens is this fluctuation field zeta epsilon t, it converges in law to a Gaussian field. So a limit fluctuation field of zeta t, which satisfies some sense. So please don't ask me what sense. This is getting way over my depth, but the way to give a meaning, this is going to be a noise. I'll define in a second. I have no idea how you give a meaning to this equation. It's much too hard. But what you can do is to write down the equation on the covariance. Right, that two times is something I understand. I won't do it because it's a little bit messy to write, but this you can solve. Okay, so this is the stochastic equation, but which I don't understand. But you can write down the equations on the covariance, and this you can solve on a short time. And so what are those guys? So let me go back to my picture to try to understand those guys. So remember here I have a time going from 0 to t. So at time 0, I have my tensor product essentially up to exclusion. So all these particles here at time 0 are distributed according to x0. Then you evolve time. What happens to those particles? Well, they're all distributed according to f. So as long as this doesn't happen, everyone is distributed according to f, which means that the equation on this zeta here will be a linearized Boltzmann equation, linearized by f. Each time a particle hits another one, okay, the distribution is f. So I'm just linearizing the Boltzmann equation around f. Until this happens. this happens at a random time, random angles, random velocities. And like we did yesterday, we can reparameterize this random time, random time by the cross-section, which is gone here. So in the end, this is what happens. This guy is a noise, which is due to collisions and overlaps. This guy is a linearized Boltzmann equation. So LT of a function g, by definition, will be minus v gradient x g. This is the easy part of Boltzmann, plus the linearized version of the Boltzmann operator, which is something like f prime 1 g prime 1 f prime minus, I forgot, okay. And then you have the cross section, dv1, dv2, d omega. Okay, so that's just a linearized Boltzmann operators, that's fine. Around f. And d eta here, so is Gaussian, quite in space-time. Of course, it's not quite in velocities because when two particles collide, their velocities jump. For the covariance of this noise eta satisfies. And so we've seen what it should satisfy essentially. I'll try to convince you that it's linked to this thing here. So if you look at the expected value at 2 times 2 positions and 2 velocities, the function phi theta 1 will be enough, and the same for another time, other position velocities, other function. So as I said, it's quite in space-time. You have correlations, which are due as usual to recollisions. And then what you get here is f prime 1 or f1 f times v prime 1 plus v prime minus v1. And if I call this delta phi, then you also get delta h. This is very strange, maybe. Well, it was very strange to us when we read Spohn's book, because that was actually conjectured by Spohn. And the first time we saw that in his book, we were totally, we didn't understand at all why recollisions would play any role. But actually, it's important. It's obvious when you think of it, when you understand this picture, that recollisions are very important at the level of fluctuations. And they're the ones that give a noise which it didn't have initially. Right? And what's nice about this theorem is that initially you have a purely deterministic system, and the fluctuations satisfy a stochastic. That was that's nice, and so that was already understood by Spohn a long time ago. And actually, he proved this result at equilibrium. If you assume that your initial data is just a Gaussian, the Maxwellian, then they prove exactly this theorem for a short time. The linearizer operator is very well known in that case. Everything's known about it. And more recently, with as usual, Thierry, Laura, and Sergio, we proved that at equilibrium, actually, you have the same result for any long time, arbitrarily long, and even going to infinity as epsilon goes to 0. You can scale the time with epsilon. So if you decide that 3 logs are still going to infinity.
No.
Sorry? Okay, you go out. Right, so except for Scott, if you decide that this is going to infinity with mu, so you like 10 to the 100. I don't like 10 to the 100. It's too small. But okay, so in that case, so we do get a theorem which holds for that time, and we're still happy because in that case, if you again, we're still happy because that gives you hydrodynamical limits, and so that's in progress. But we were able to find fluctuating hydrodynamics, linear hydrodynamics, starting from the deterministic particle system. Okay, so we have a result saying that you start with your particle system purely deterministic at equilibrium, okay, not near, at equilibrium. Then when epsilon goes to infinity, your fluctuation field, if you project it onto hydrodynamical modes, converges to a Stokes Fourier equation with fluctuations. Okay, so a stochastic Stokes Fourier equation. Okay, that's all. 6 minutes. Okay.
Can you remind me what is H in the formula above?
There's no H. No, it's psi. There was H. So it's the same. It's an H erased with a sign on top. Are there any questions on this? Okay, so just to finish what I wanted to talk to you about. So open problems, there are millions of open problems. As usual, I mean, the Landford time is this, here we get a short time, which is slightly worse in Landford, but not much worse. It's essentially the same time as Landford's time. So is there any way of doing better? Is there any way of solving this equation better than what we do? We solve it in the mild form on the covariance because, okay, I don't know how you can solve this equation in any other way. LT is a horrible operator, actually, right? If F is a Gaussian, then this is a nice Q, not Q, self-adjoint operator. You know everything about it, so you can really solve this equation. But if F is anything, then not often in stochastic equations, you can look at that equation. So now the last thing I'd like to talk about today are large deviations. Sort of the next question in the program is to say, what happens? Okay. So is there any possibility that your empirical distribution would be actually very far from F? So take any function phi, which is not F, the solution to Boltzmann, and is that exponentially unlikely? And so you can prove that it is, and I'll try to explain how you do that. And the way of doing that, usually I guess people who do that in probability theory would say, well, just you have your function phi, move around your particles initially and to find phi. Okay, but you can't do that. I mean, there are too many particles, it's too unstable. And I think there's no way of going back to the particle system and trying to hit anything else than the Boltzmann equation. I wouldn't know how to do that. So the way we proceeded was using the exponential moments, which I defined before, in a special setting. So let me give myself some function g, and so the exponential moment will be, as I said before, the log of the exponential of the expectation of the exponential of the sum of pi epsilon e of g. And now let me choose a special g, which depends on the whole trajectory of my particle z. Okay. And by definition, and also can depend on time, simply I'm acting on the final time at position z of t. And I'd like also to know what happens on the whole trajectory. Okay, so this is sort of for technical reasons. We like to put the transport here. It's like filtering out the transport thing. Doesn't really matter, but I want to know what happens for g or for its transport on the whole trajectory. So let me choose this for my function g. Okay, that gives me a functional, and because of the formula which has disappeared now, I knew this was equal to something like 1 over n, the integral of the cumulants applied to this function here now g. And now the first thing you can do is prove that this is of size factorial n, which is very nice because it tells you this series converges. Why is that true? Well, if you believe what a cumulant is saying I have n particles and they all see each other at some point. Not an n-point correlation function. A cumulant, just like F2, they all see each other. So for n particles to see each other, essentially, it's like a tree with a binary tree with n vertices. It's essentially this n to the n minus 2, essentially factorial n. So if you believe that, then you believe the series converges. So you believe this guy has a limit, and you can write down, and that's a nice part of the theory, is that you can write down an equation on this limit, and I'll be essentially done with that. This limit I satisfies the Hamilton-Jacobi equation under the same assumptions as usual for a short time as usual. You get an equation which is di over dt. So it's a slightly frightening equation because this guy is a functional, right? On function, so it's a functional. And it satisfies the Hamilton-Jacobi equation in the sense of functionals. So if you're scared, you can imagine how I am. So you just take the derivative of I at the final time g of t, computed at z1, z2, because this becomes a function actually. And then you apply this to the delta, which we wrote up there, delta g minus 1, and you integrate against the usual measure. And this is the equation I satisfies. This is a beautiful Hamilton-Jacobi equation, which is horrible to solve. We can only solve it in the class of analytic functions. That's why short time again, as usual. What's very nice about this equation is that if you start taking derivatives with respect to g, this is very classical for people who know, you get all the cumulants slowly. So the first derivative will give you the Boltzmann equation, actually. If you believe me, this is f, actually. Okay, so if you compute the first derivative of this guy, you'll get exactly the Boltzmann equation. If you compute the second derivative of this guy, you'll get exactly the covariance equations. Okay, and so on and so forth. So all this you have to prove, but it's hidden behind all that. And then just to finish, you have a large deviation functional. So this is just to go back to Scott's talk this morning. It's given by a transform, which I'll let you guess. F of t and phi is something like the soup of, so I'll try to get this right, minus integrating in time and space, phi dtg plus v greater than xg, soup of all g's, minus plus phi of t g of t minus I of t and g. Okay, so it's a Legendre transform in some sense, right? Those scalar products here. So, okay, all this can be proved, and I'll stop just by mentioning that this functional probably looks essentially horrible. Everything looks a little bit horrible, but it's equal to another functional. So it's equal to, but I'll just give another name anyway. Okay, another functional which was found by Fredun, was that Camus? Not sure about the H's. I think something in 2000. I think that was, I can't remember exactly the year. He was looking at a stochastic particle system initially. And so he proved a large deviation principle with a functional, which turns out to be, after some work, exactly this one. Which is interesting because it's telling you if you put noise at the beginning or no noise at the beginning, at the end you have the same large deviation principle, actually, which was a nicer point. So they're equal for very restricted classes of functions and things. But still, it's the same one, whether you put a noise or not. In the end, you get the same function. Okay, so I think I'll stop here. Thank you for your attention.
Other questions or comments?
So the introduction of irreversibility again, it seems like the main thing when you're looking at this tree diagram structure is about whether or not these recollision events have any impact, right? It came down to the difference between those two. Mm-hmm. Is there like an intuitive reason why that introduces an arrow of time? Like, I don't quite see how that naturally induces like an irreversibility structure.
Yeah, so let me try to make this more precise. I couldn't get my sentence right before, but I'll try to get it right this time. So you can write down the Landfall Theorem as follows. Take your initial data, which is, as we said. I said before, f of t converges to f in L infinity. Then I said f n times, the endpoint correlation function converges to n copies of f almost everywhere. I said that because I didn't want to be too precise. Now, if you want to know what that almost everywhere is, it's much better than that. The set on which you have convergence is a set of configurations such that if you look back in time, particles will not see each other. That's the theorem. So you take a time t configuration, look backwards, they haven't seen each other, the theorem works. And on the other hand, your initial data is set up so that they do have collisions. Okay, so you just can't write down the theorem the other way around. It just doesn't pay. Or time is just I've looked back. So
yeah, thanks. So I have a short question on the CLT. So I assume that when you prove this is based on a tightness or martingale convergence argument. So which would make it a qualitative statement of convergence. So is there any hope at all to have a quantified statement?
It is quantitative.
Oh, it's quantitative already.
Yes.
Okay.
It has to be, if you believe this, then it has to be, I don't know if it's.
So what's the rate that you would see there?
Probably 1 over log. I don't know. I can't remember. But you have a rate which is essentially almost a small O of 1, except you can quantify this as maybe 3 logs or something. It's very bad. Okay, but there is a rate, and so to prove that, what you do is you first take fixed times, you compute the covariance, and then you have a tightness argument to get the whole thing for continuous times, and everything can be computed with error terms.
So for your I don't know, stochastic PDE or whatever, if L is smoothing, life is much better. And I can never remember for the Boltzmann collision operator what it looks like when it's smoothing, what it looks like when it's cut off and whatnot. This is like the regular one with you have smoothing, so
Yes.
L helps you have. Okay.
It helps if you have Gaussian, yes, definitely. If you have F, I mean L, if you take the linearized operator against around M, then it is smoothing. You have lots of things to say.
Yeah.
But here with F, I don't know anything about it. And I don't know if you have the same kind of thing for other collision kernels.
Were you talking about smoothing with respect to singular kernels? Or did you mean that?
I just mean if you get rid of the noise, isn't that smoothing? I mean, it's a PDE, right?
Right. I don't think L is smooth, is it?
L has a special graph, but it's not smoothing in a sense. It's not like if you have the cutoff equations or something like that. Is that what you meant?
So
What
if
do you
you
mean by
don't cut, so for the usual Boltzmann equation,
Yeah.
it's not, at least, okay, if we're talking about the same thing, I never know. Right, you have, I don't know, DeGiorgi stuff and Schauder and blah, blah, blah. So you
That
can,
doesn't work for Boltzmann with hard spheres.
okay.
Yeah. All those results with Ambert and Sylvestre and Wu, and those results are not for hard spheres. And it doesn't work actually for hard spheres. We've tried. This equation is not smoothing in the sense that you don't have those properties. Well, all the shadow estimates and everything just fail dramatically for hard spheres. Or you don't even have there are problems. For instance, you have smoothing in velocities. You don't have that here. And in X, you just have a collision.
Okay, maybe I'll come bother you.
Sure, there are some averaging lemmas and things like that.
Sure.
Yeah, we can talk about that.
There are other questions, comments? If not, then let's thank Isabelle
Thank you.
again.